In highway traffic dynamics, a single braking event can trigger a chain reaction known as string instability. One car slows down, and the subsequent vehicles overcompensate, creating a shockwave of stop-and-go traffic that ripples backward through the flow. Vehicles equipped with adaptive cruise control attempt to manage this through automated following distances. When set to a short gap, these systems allow dense packing that pushes the theoretical capacity of a highway up to 2,900 vehicles per hour. But tight vehicle packing degrades string instability. If a lead car taps the brakes, the lack of buffer space forces the trailing car to brake much harder. The deceleration multiplies, intensifying the shockwaves. Setting the system to a long gap provides a physical buffer that absorbs these braking shockwaves. However, that safety margin chokes overall highway throughput down to just 1,500 vehicles per hour. Current autonomous vehicle implementations force engineers to pick one of these parameters and maintain it throughout the drive. Relying on a fixed following distance locks highway management into a zero-sum trade-off, where increasing capacity requires a sacrifice in flow stability. In macroscopic traffic flow theory, system health is measured by analyzing how vehicle density dictates the flow rate. When a highway transitions from free-flowing to congested and back again, it creates a loop on the graph, a phenomenon known as hysteresis. This scatter plot maps that relationship. The red data points track a highway where vehicles maintain uniform short gaps, and the blue tracks uniform long gaps. Both approaches suffer from pronounced hysteresis loops as congestion intensifies and recovers. To address this, researchers trained a double deep queue network, or DDQN, to dynamically toggle the gap setting of a single connected vehicle in the flow. The gray curve tracks the result. By switching the behavior of just one vehicle, the DDQN agent flattens the hysteresis loop compared to the static baselines, maintaining higher flow rates during both intensification and recovery. Crucially, this agent does not control raw, continuous acceleration. It operates strictly as a high-level supervisor, selecting between the manufacturer-calibrated short and long preset distances. Macroscopic traffic hysteresis can be mechanically unraveled. The data indicates the solution relies on intelligently toggling existing discrete systems, rather than inventing entirely new methods of continuous vehicle control. How does a reinforcement learning agent optimize a complex traffic system using nothing but a binary switch every 5 seconds? This diagram outlines the neural network architecture. On the left side, we see the 5x1 state vector the agent uses to evaluate the environment. The agent monitors 5 variables: the subject vehicle's speed, the speed of the lead vehicle, the microscopic headway, and the average speed and density of all traffic within a 1-kilometer radius. These variables pass through 4 hidden layers of neurons before coalescing into a strictly constrained 2x1 binary action space. The output is a simple choice: short gap or long gap. The network is guided by a scalarized reward function. The agent is penalized for high travel time rates and high acceleration noise. These competing objectives are mathematically weighted at 0.1 to balance efficiency with flow smoothness. By stripping away low-level mechanical commands from the action space, the architecture isolates the logic of traffic flow optimization. Beyond the theoretical architecture, we can evaluate the agent's live temporal performance over a simulated episode of 50,000 time steps. The middle graph tracks the vehicle's speed as it hits a congestion event, marked by a massive dip in velocity, starting around step 10,800. The event is split into 4 distinct phases. The heaviest congestion occurs during Phase 2, the intensification period, and Phase 3, the recovery period at the bottom of the V-curve. Note the sparse frequency of the agent's actions during these phases. It only switches gap settings roughly 1 time per minute, an intentional constraint designed to prevent erratic chattering between states. The acceleration graph reveals the physical reality of the policy. Despite navigating stop-and-go waves, the DDQN keeps the vehicle's deceleration within safe, manufacturer-defined bounds. Effective traffic mitigation relies on sparse, calculated interventions, rather than constant micromanagement of the following distance. We can now identify the specific environmental trigger that causes the DDQN to toggle its setting during the heaviest congestion. This chart isolates the agent's gap setting preference based directly on the behavior of the car immediately in front of it. When the lead vehicle accelerates, the DDQN commands a short gap. It exploits the higher acceleration parameters of the short setting to quickly pack the lane and maximize throughput. But the moment the lead vehicle decelerates, the DDQN snaps to a long gap. It leverages the larger temporal headway to absorb the braking shockwave and preserve string stability. This reactive logic contrasts with the rigid, uniform behavior of human drivers or static cruise control systems. The DDQN reconciles the capacity and stability trade-off by slicing time into discrete phases, deploying the specific advantage of each gap setting in alignment with the lead vehicle's movements. Does this asymmetric policy maintain its effectiveness when applied to multiple autonomous vehicles simultaneously? This graph tracks system-wide performance as the market penetration rate of DDQN-equipped vehicles scales from 25% to 100%. The top gray line represents the DDQN's increasing episode reward over the baseline static approaches. At 100% market penetration, the results show a dual improvement. The DDQN maintains the high-speed efficiency of the short gap approach while simultaneously reducing acceleration noise by nearly 60%. These agents execute this policy in a decentralized manner. They do not need to communicate with a central server. Instead, each vehicle reads its local state and executes the learned policy independently. This demonstrates that independent, decentralized agents can successfully coordinate to improve macroscopic traffic flow. A primary barrier preventing reinforcement learning from being deployed in production vehicles is validation. It is difficult to guarantee the safety of an agent that has direct, continuous control over acceleration. Treating manufacturer-calibrated ACC systems as a discrete action space bypasses this regulatory and safety bottleneck. The result points toward a reality where existing commercial vehicles can mitigate traffic waves simply by toggling their built-in systems. By bounding deep learning strictly within the proven safety limits of existing hardware, this architecture offers a feasible pathway for AI-driven traffic optimization.